Good
Okay.
morning. Have a great day wherever you are. I'm Harindra Lal. Today my duty is to introduce Professor K.C. Ravindranathan, who is taking over as the chair of the Intersociety Activities Committee of IEEE Kerala section, who will be doing the role of the webinar in my place. Dr. K.C. Ravindranathan, a senior member of IEEE, fellow of IETE, fellow of IE, and chairman of the IET Trivandrum Center. Now he is the chair of the Intersociety Activities Committee, Kerala State Section also, IEEE Kerala Section also. It's my present duty to welcome Dr. K.C. Ravindranathan to our midst to take over this job.
Thank you, sir.
Now, I invite Sandra to take over and conduct the proceedings.
Thank you so much, sir. Am I audible?
Yeah.
Yeah, you are.
Okay, sir. Good evening, ladies and gentlemen. Honorable Chief Guest of the Day, Mr. Raghukumar K. MBA, former Head of Transmission, Qatar General Electricity and Water Corporation. Respected dignitaries, guests, volunteers, and all the participants, a very pleasant evening to you all. I, Sandra Baiju, feel extremely privileged to welcome you all to the 93rd Talk of Intersociety Weekly Webinar Series, jointly organized by IEEE Kerala Section, the Institution of Engineers Kerala State Center, Computer Society of India Trivandrum Chapter, Project Management Institute Kerala Chapter, Internet Society Trivandrum Chapter, Vakkom Moulavi Foundation Trust Trivandrum, Life Member Affinity Group IEEE Kerala Section, IEEE Engineering in Medicine and Biology Kerala Chapter, the Institute of Electronics and Telecommunication Engineering. Before we begin the session, I would like to kindly bring your attention to the feedback link that would be provided along with the mail posting the Zoom link. Link to the recordings will be given to those who send their feedback. Those who want certificate of participation may indicate their requirements in the feedback sheet. And except for the speaker, all participants, please make sure that your audio and video are off throughout the session. I also request all the participants to put your actual names in the Zoom platform that was used while registering for this meeting. And after the session by the speaker, we will be having a formal question answer session. So all participants are welcome to post all your queries and questions in the chat box. And the selected questions and queries will be addressed by the speaker after the session. Participants can also type in their queries in the chat window in case of any technical issues. Now, moving on formally, I welcome Professor K.C. Ravindranathan, PhD Chair, Intersociety Activities Committee, IEEE, to welcome the virtual gathering. Sir.
Thank you, Sandra Baiju and Mr. Saju. I indeed feel privileged and honored to welcome the August audience today assembled here to listen to the 93rd Intersociety Weekly Webinar Series. This is a unique feat achieved because of the relentless spirit of our senior life member, Engineer Harindra sir. And today we are attending the 93rd lecture in the series. He had been doing this task of organizing and conducting Intersociety Weekly Webinars right from April 2020. He has reached a milestone which nobody else can cross. This is the 93rd lecture is being delivered today. And from the 95th talk, I'll be taking over the task of coordinating and organizing these talks, which are a special brand ID of the IEEE Kerala section and other sister societies. Right? Let me get into my task of welcoming our honorary guest speaker, Engineer Raghukumar, who is an electrical engineer, and he has several years of experience with Qatar Electrical General Electricity and Water Corporation. And first of all, I invite Raghukumar. But I should also invite and place on record the relentless team spirit as shown by Engineer Harindra sir. So I also welcome Rendilal sir to this meeting once again. I also welcome all the student team members, starting with Rashta Sajju, Sandra Baiju, Gogul, and others who have shown an exemplary team spirit and have rendered their relentless support in conducting these webinars every week without a single Wednesday missing out. So I welcome all the listeners. We have more than 30 participants right now. It may increase slightly when we proceed further. So I welcome all the listeners, attendees, and other friends of IEEE, IET, IE, Institute of Engineers, and all other sister societies which are participating in this weekly webinar for the past several months. Welcome once again to all. Over to Gogul, please. Gogul.
Yes, sir. A very warm welcome to one all present here today. Today we have with us Mr. Raghukumar K. to the keynote on the topic Conditional Monitoring and Health Assessment of Power Transformers. Mr. Raghukumar sir is the senior member of IEEE and he was former head of Transmission Qatar General Electricity and Water Corporation. A hearty welcome to you, sir, once again. Sir, I kindly request you to take over the session.
Thank you, Google. Am I audible now?
Yes, sir, you're audible.
So thank you very much for the welcome, Professor K.C. Ravindranathan, and the introduction by Mr. Gokul. And I have to thank Harindra sir. He was behind me, and I'm very, very happy to present this. And all the credit goes to Harindra sir, who was instrumental in me to do this talk. Thank you, sir. Basically, today's talk is on condition monitoring and health assessment of transformers. It's from practical experience gained over a period of time. We were doing this from around early 2000 onwards for the last 20 plus years. And the condition monitoring has evolved over a period of time. And here, today I'm touching up only on transformers. This condition monitoring is done for transformers, switch gears, cables, overhead lines, for all grid assets. So without much ado, let me go towards the condition monitoring part. There is Mr. Naveen Raghu. He is the head of condition monitoring section in Qatar Electricity. He is an expert in this asset management. Without his contribution, I could not have made this presentation. Thank you, Naveen, for your support. The photo of what you see on your left is a 2000 MVA transformer, 765 kV class, and all types of monitoring whichever is available is used in this transformer. This is located in South Korea. It's a Hyosung transformer, and the life of a transformer is dependent on thermal life. That is, the insulators of the insulations. Thermal life is very important. Next is the dielectric life of the oil, mechanical life, the mechanical integrity. After a few short circuit, the mechanical integrity need to be checked, and accessories play a big role. OLTC is the only moving part in a transformer, and the bushings. Bushings are common failure points. For those who are present, who are not very familiar with the transformers, I'll give you a brief video on what is inside a transformer. For this, I thank Hyundai who has provided me with this video. This is a core stacking process where the core is initially stacked.
So the video is not displayed.
Once the core stacking is over, the basic insulation material is put, and then one by one the winding and in the insulation goes inside. In this particular case, there are 3 windings: HV, LV, and tertiary windings for 3 phases. The next stage is taking out the lead terminals from the LV side. This you can see now, this LV side terminals are being taken out. And next is the HV side, and the tap changer gets connected to the HV side. This is the tap changer is coming into place.
Yes, Mr.
The video is not displayed, sir.
The whole winding process is over, and now the whole winding will go inside the tank. Did you notice the shape of the tank? There is a reason for this shape. Next comes in the bushings. HV and LV bushings are in place. Next, the oil connections are coming up. And because this is a big transformer, there will be 2 sets of conservator banks. So this is the final version of this transformer. I hope the basic understanding of the transformer is clear for everyone. Go back to the presentation. I talked about the shape of the transformer. See, the reason behind the shape of the transformer, why the shape is narrow and then long, is all dependent on the railway tracks available in Europe at that period of time. And these transformers had to be shipped on in railway tracks, and the shapes were made compatible to the tunnels in the track. This is the reason why most of the transformer, what you find, is long and narrow. See, this transformer is a failed transformer, and nobody wants to see a transformer in this condition. The windings are being lifted up to understand what went wrong. So now the question is, why is condition monitoring required? Condition monitoring is carried out to prevent failure of critical transformers. And the maintenance has to be made cost effective. You cannot have a very expensive maintenance procedure. So a cost effective maintenance is what is required. Then awareness of the operational capability. Once you have the complete information of the system, the operation, how much it can be loaded, whether it can be overloaded, these kinds of decisions can be taken if the present status is well known. Then reliability of an expensive asset is assured by going through condition monitoring. And in the long run, you get enough time to plan for replacement. Now the question arises, which transformers to monitor? See, Qatar may be having about 900 plus transformer in the system, and it's impossible to monitor. I'm talking about only the transmission side. In the distribution, there are 20,000 plus transformers. In the transmission, we cannot afford to monitor all the 900 transformers. So what we are doing is, we are dividing the transformers into 3 different categories. The one is the critical transformers. The failure of the critical transformers can impact grid stability, and it will be a major revenue loss in case of a failure. The second set is important transformers. The failure can have significant impact on the revenue. Normally, this interbus transformers comes into this class. Next is the unimportant transformers. The failures are low impact. So what we were doing is, all transformers which were above 100 MVA was being monitored, continuously monitored. And below 100 MVA, transformers were partially monitored. And there are certain below 100 MVA which is fully monitored. Those transformers were the ones which are underground. We had about 12 to 13 underground substations. And all the underground substations are very critical because any fire inside is dangerous. So underground substations are continuously monitored, even if the transformer size is small. And the smaller transformers are rarely monitored continuously. Only offline condition assessments are being carried out on the smaller ones. To understand things easily, the transformer's life testing can be compared to a person's testing. See, we can do our medical test by taking a blood sample. The transformer instead of the blood, the oil sample is taken. The blood sample gives you a general idea about your health conditions. Similarly, a transformer's life can be understood from the analysis of the oil. Once the oil results are out, the physician diagnoses what is your problem and gives you a certain regimen. Similarly, similar role is played by the transformer engineer who does the initial diagnosis, and when the condition is more serious, it is referred to a specialist. Like in your case, from a physician, you move to a specialist. Like that, we move to a transformer expert for advanced diagnosis and confirms the maintenance need. It's like a second opinion. And in the third stage, where you have to go in for an internal inspection or intervention, like what a surgeon does, we have to call in the original equipment manufacturer or a third party capable of doing this. Normally, original equipment manufacturer is preferred since the third party can also do the job, but they will not be having the required spare parts to do the repair work. And lastly, even with all the condition monitoring done, certain transformers do fail. And after failure, the pathologist's role is taken over by the senior transformer expert who removes the winding, have an internal inspection to find out what actually went wrong. So online monitoring is a continuous data measurement. It gives you an early warning system. And diagnosis is the health assessment. It's a decision support system which helps you to maintain, refurbish or replace decisions. Monitoring basically measures and stores raw data. Compare the values with preset limits. Alarms when measured values are above a set limit. In expert systems, software takes the input from the monitoring systems, analyze this data, indicate reasons for the alarm, give advance warning that a problem is developing, and the remaining life of the transformer is calculated. What kind of monitoring can we do? Most of the monitoring is non-intrusive while the transformer is still running. The first one is a visual inspection. And the next stage, we go in for an infrared scanning. And the last stage is dissolved gas analysis. And normally, a PD measurement is carried out in certain very important transformers. Visual inspections can find out defects like oil leaks, bird nests, marshalling kiosk, loose connections, etc. There was one case in Qatar where an oil leak inspection, visual inspection saved a bushing. It was a 315 MVA transformer, and during the visual inspection, it was noticed that oil was coming out of a bushing's test trap, and the leak was a bit serious. And immediate action was taken, and further inspection was carried out, and it was found that the bushing was defective and need to be replaced. And this bushing was not an external bushing. This bushing was going inside a GIS. So a damage could have damaged not only the bushing, even the GIS compartment could have been damaged, and it would have been a major disaster, and it would have taken more than a year to repair and replace. Just because the visual inspection identified the problem, immediate action could be taken. The winding, the bushing was replaced, and the transformer was brought back into service. Next is this looks a minor issue, like a bird nest. No, it's not a minor issue. See what happens with open bushing transformers. This bird nest comes up, and then the bird is not the problem. There are cats coming looking for these birds. The cats jump over the transformer and cause a direct short circuit. And this has also caused tripping of the transformers. And the loose connections inside the marshalling kiosk is also a major headache. The control cables can get loose and give a short circuit, and without a fault, the transformer can trip. Next comes this infrared scanning. In infrared scanning, thermal images are taken using an infrared camera. This is normally done during a peak load times. Normally in Middle East, it's a summer is a peak load. This identifies cooler defects. It has been detected after years. Certain coolers were not opened, which affects the cooling efficiency. This can be detected only in the thermal imaging. And certain other hotspot issues also can be identified with this infrared scan. Next comes for this bushings. For the overhead bushings, what you see here, thermal scanning is done, and delta T, that is the temperature difference between the two bushings, is checked. And if the temperature difference is within 10 degrees, it's considered normal. But if the temperature difference goes up to 20 degrees, then the monitoring is continued. And if it is between 20 to 35 degrees, then the monitoring frequency is increased. If it is greater than 35 degrees, immediate action is required, and shutdown is arranged and checked. And most of the times, it has been found that a loose connection was the reason for the overheating. So this infrared scanning cases are like this. Next comes this online monitoring. This is an 800 MVA transformer where you can physically see certain things in this. This is that online monitoring device, and this is a monitoring system where all the data from all other sources comes here for monitoring. And this information is taken inside the control room and to a HMI, and that HMI has got the software for all the analysis purpose. And what is being monitored is dissolved gases. There is a decision you have to take whether you want to monitor 1 gas, 3 gas, 5 gas, or 9 gases. In this particular transformer, 9 gases are monitored. Humidity of oil, oil temperature, current and voltage are recorded. Bushing tap PDs are measured continuously. Tap changer positions are recorded. Tap changer motor drive currents are recorded. Fans and pump status are recorded. And hotspots, there are two ways of finding out the hotspot. One is theoretical calculation. Second is physical sensors kept inside the transformer. Fiber optic sensors are kept inside the transformers. From this, direct hotspot temperatures are measured. So these are the basic online monitoring systems. These are some of the equipments which are used for online monitoring. This Kelman Transfix is an equipment which works on photoacoustic principle. And Serveron is an equipment which works on gas chromatograph. Gas chromatograph has got a maintenance issue in the sense that it needs a carrier gas. Helium is a carrier gas here, and this helium need to be replaced every 2 to 3 years. And once you replace, calibration is required. This equipment does not require any calibration. It works on a photoacoustic analyzer, and there is no carrier gas involved in this. These both equipments can get 9 gases checked. In smaller transformer, we fix up this hydrogen sensors. This can monitor only hydrogen and moisture. Most of the parts has got hydrogen in it. And this is how the oil is taken up into the analyzer. See, from the top valve, oil is taken and then it comes into the analyzer. And once this process is over, it is pumped back to the bottom valve. So no oil is lost during the analysis process. These are the gases which normally we detect during the condition monitoring. There are 9 gases what I talked about: hydrogen, methane, ethane, ethylene, acetylene, oxygen, nitrogen, carbon monoxide, carbon dioxide, and then total combustible gases are calculated. These combustible gases are carbon monoxide, hydrogen, acetylene, ethane, ethylene, and methane. The fault intensity is dependent on the total amount of combustible gases. And moreover, this process is a trending analysis. Over a period of time, what is the rate of change of gases? This is a practical example of monitoring success. This was a 150 MVA transformer. And this 150 MVA transformer was giving Buchholz alarms. The gas was not sufficient to trip, but it was creating Buchholz alarms. You reduce the load, the alarm was disappearing. This transformer was a very important transformer, and we couldn't switch it off immediately. So what was done was a continuous monitoring of the gases was done for a period of 1 week. This was this particular transformer did not have condition monitoring at that point of time, and physical oil samples were taken and checked every day. And at different loads, the load was adjusted, it was reduced and increased and checked. And finally, we arrived at a conclusion. See, if you look at this, this is the most important gas, which was above the warning limits. This is ethylene. And ethylene's presence is normally when there is a high temperature fault, like above 700-degree faults are there. Later on, over a period of time, it was assessed and found out that 60 MVA, the transformer can be safely operated. And we kept that load at 60 MVA, and the transformer was operated until an expert arrived from the manufacturer. And then an internal inspection was carried out. Those days, internal inspection means you have to remove oil completely. Then one person goes inside the transformer, physically checks, comes out, and then finds a solution. In this particular case, it was eddy current issues in a shield which was loose, which was corrected. And later the gas formation was completely stopped. If the monitoring was not done, this would have led to tripping and it would have been a major incident. And DGA gives out different gases. And it is very difficult to say what the fault is just from the gases only. If you look here, you can see hydrogen is present in most of the faults. And also similarly, methane is also present everywhere. So the answer to what the fault is, you have to get it from an expert. And there are certain softwares which can give you the results. And there are certain normal values given in IEEE standards, where, for example, if you take hydrogen, 100 ppm is a normal value, and 100 to 700 range, it's a caution value, and above 700 is warning. But IEEE is very, very conservative. So this 100 is not very practical always. It is load dependent. If you look at it, in summer, the hydrogen level increases, in winter it comes down. So we used to keep it up to 200, 250 as normal, and then in winter it will definitely come down. And how to find out what the fault is. So IEC and IEEE has got relevant standards, which gives you some kind of tools how to find it out. There are three methods basically used. One is called a key gas method, where only a single gas concentration is considered as for the fault finding. Like in the previous case, which I showed you, ethylene. Ethylene concentration shows that it is going to be a high temperature fault. Acetylene shows like it is a arcing fault. Things like that is identified from a key gas. Then there is another one called a two gas ratio, which is called Rogers ratio method. The third method, which is most popular, is a three gas ratio method called dual triangle. This is the dual triangle, and this person is the person who developed this system. He is Dr. Michael Duell. He was working for Hydro-Quebec, and he travels around the world and trains people. We all received our initial training from this guy. He used to come and explain things, and he is an expert in the oil system. And in dual triangle, what happens is, he has given a triangle with three gases, methane, ethylene, and acetylene. Percentages are calculated and on a 3 coordinate basis, and where the 3 coordinate meets in some point in this triangle, and that is the fault. These faults are given D1, D2, DT, T3, all these things are explained here. So suppose if it meets a D2, it means it's a high energy discharge. Like that ethylene concentration issue, it can be a high energy discharge. And if it is meeting at this point, it's a partial discharge, like that. The disadvantage, there is one disadvantage for this method. This method, you have to be initially sure there is a fault present. Otherwise, what happens is, dual triangle does not have a location which says no fault. Every point in this triangle is a fault. So you have to be initially sure that there is a fault present to use dual triangle. Next is we do some kind of offline monitoring. Offline analysis is required to find out physical conditions of the oil, like acidity, moisture, interfacial tension, breakdown voltages, inhibitor content, oxidation stability, corrosive sulfur, degree of polymerization, furfural, PCB, etc. Each is a huge subject. Like corrosive sulfur is a big issue, which is created by a substance called DBDS in the late 90s, early 2000, when the transformer requirement was very high, and the oil was passivated with DBDS, which started giving problem of copper sulfate formation and rusting. And there was sudden transformer failures, and on investigation it was found out this DBDS was the culprit. And nowadays each transformer oil is tested to avoid this corrosive sulfur. Then color, viscosity, flash point, etc. And DG is again rechecked offline to confirm with online measurement that it is correct. See, color is something which you can easily identify with. See, these are samples of oil with different colors from good to bad. The good oil will look like that, and the worst oil is looking like this. Why this oil color changes is due to sludge formation. And once the sludge is there, the cooling efficiency is reduced drastically. How do you reclaim the oil? Or the oil can be filtered, yes, but filtering can remove the gases in that, but it can, and the moisture can be removed. IFT can be improved, VDV can be improved, but it cannot change the color and it cannot change the acidity. These two cannot be reversed by oil filtering. So what is the solution? There are two solutions. One is you replace the oil completely. The second is called oil regeneration. This is an example of an oil regeneration. Oil regeneration can be achieved at almost half the cost of a new oil. The equipment comes in a container, and this container has got two compartments. One compartment is where the oil reclamation process takes place, and the second one is a laboratory setup where the oil can be continuously tested. This is a two-part process. One is oil filtering, and the second is it is passed through columns of fuller earth. And this is what is removing the acidity, sludge, and stuff like that. These are the set of oil samples which have been taken during the process. You can see the change in colors. And this was the initial oil color, and this is the final oil color. The advantage of this one is the whole process is carried out while the transformer is live. We switch it off only for one time for connecting the hoses and the second time for removing the hoses. And the oil circulation is going on continuously on a live transformer. And there are certain equipments which are connected to the inlet and outlet to avoid entry of air into the transformer. And this is fast also. These are huge machines with a capacity of over 5,000 liters per hour. And on a small transformer, hardly 20,000 liters of oil will be there. And within one day, the process will be over. The same oil, if you want to totally replace, it's a 1 week job. And it's not a question of job alone. This oil which is removed, disposal is a big issue because of environmental factors. That oil regeneration avoids all this. This is an interesting part. The internal inspection. See, suppose you have identified a fault in the condition monitoring, and you know it is inside the transformer. How do you solve the problem? So normally OEM has to solve the issue, but the problem is we don't know exactly what the problem is internally. The two ways of solving the problem is, one is giving a contract directly without knowing what is the issue, where the contract value will be very high because the tenderer doesn't know what exactly is the problem. He is expecting the worst and will charge you heavily. The second is a two-part contract. The first part is an internal inspection, and based on the internal inspection, we go in for the second contract. With government utilities, you know the difficulties of getting contracts through. The first contract may take a year, the second contract may take another year. So 2 years, your transformer is lost. Now, ABB has come out with a new technology. ABB has been taken over by Hitachi, I think. Now it's called Hitachi ABB. This is a robot. It is comparable to a drone. If you compare it with a drone, it flies in the air. ABB's robot swims in oil. This is the robot, and oil has to be removed only up to the top of the transformer. Then this is introduced inside. Just you can see a hook inside, and then it's left inside. It swims inside. Afterwards, the control is from a control room. This person is controlling from the control room the robot's movement, and he can see what is inside the transformer, and the whole process is recorded, and we get the full recording for us. And what this is seeing is here. See, this is a robot going on an internal inspection. This photo is taken from his display. And these are tap changer contacts. It goes near each and every contact and checks every contact for loose connection or flashover marks or anything. Like this, it can go over the complete transformer and exactly pinpoint what the issue is. Then it becomes much more easier to award a new contract, or the scope can be very clearly described. Next, we move on to condition-based monitoring. In condition-based monitoring, see, before condition-based monitoring, let us see what are the types of maintenance. One is called a corrective maintenance, where the repair is only after failure. Preventive maintenance is an old system where time-based maintenance was carried out, fixed time-based things were maintained. The issue was we were overdoing it. Maintenance was being carried out without knowing what was the internal condition. It was just a routine maintenance. Then came in the condition-based maintenance. This condition-based maintenance, the advantage is you have the condition monitoring in place and you have all the results available, and you attend only problems where the condition monitoring has told us, yes, there is some fault which is developing. So these are the three stages for a normal transformer. It moves from a normal stage to a fault progress stage to failure. We have to catch it in this fault progress stage. Monitoring catches it in the fault progress stage, which is explained in this PF interval graph. It's a potential failure to functional failure. In the first stage, here the transformer is healthy, and then it starts developing a problem somewhere here, and it starts giving you leading indicators. It is like your pre-diabetic stage. You are not at diabetic, but you have started getting symptoms that you are going to be. And then this is the point where the potential failure starts. Later on, you get a higher level of signals. So you have to catch this period. Within this time, the maintenance has to be carried out. If you don't do anything, it will lead to a failure at this point of time. So this is the principle of condition-based maintenance. So based on condition-based maintenance, we are able to get a lot of information. It's a raw data which is available in condition monitoring, which is of no value until and unless it is analyzed. So this data is analyzed and knowledge of is also introduced into the algorithms. And finally, we get it in an information which is useful for the management. The condition monitoring finally gives you an asset health index. It's a score. Basically, asset reliability and remaining life is given in this score. There are two ways of doing it. One is a color combination. The second is a 1, 2, 3, 4, 5 numbering systems. Both are used. Then asset health index is computed. This asset health index is what I told you, either numbers or colors are used. This is for the senior management level. And for the maintenance people, this asset maintenance index is very important. This index gives you for a particular zone, the whole area was divided into multiple zones. So in one zone, these transformers, what is the maintenance requirement of those transformers? It is prioritized. Which transformer is worse, which is in good condition, which need to be attended as early as possible. These scores are available in the asset maintenance index. And this asset health index is taken from condition monitoring data, offline test data, historical data, and internal inspections, if any, carried out. Finally, this health dashboard is the one which is useful for the top management and the senior level management. Here, in one single picture, you get a fleet information of the total transformer health. And then whenever the maintenance people wants a budget for a major repair, this health dashboard is a supporting document. It's a decision support system. This is how this health assessment is calculated. Multiple data are available from the condition monitoring, like your temperature data, your oil data, your loading information, your tripping information, multiple data are available. These data gives you a health indicator. And then offline data are there, like what I told you, electrical tests which are conducted, and oil analysis separately which has been done, visual inspections, thermal imaging. All these offline data are also put in. Then there is an expert opinions. There are certain knowledge base which is available. Worldwide knowledge base is available. And this knowledge base experiences are also put into this algorithm. And certain weightages are given for each indicator. And finally, we get a color chart like this. This chart gives you a picture, the good, fair, satisfactory, poor picture. And what you see on the rightmost top ones are the most dangerous ones, which can fail at any moment. So you get enough time to think whether to replace this or not. And these transformers are not attended. Only these transformers are attended initially. And if there is sufficient resources available, then this level of transformers are attended. This is how health assessment is utilized. Transformer lifetime calculation. See, data analysis is from the historical records of loading, maintenance data, failure data are all taken from the historical data. Then condition assessment data is for present status. The present status is taken from scanning, online and offline diagnostics. All this information are taken from the condition data. And the remaining life assessment is taken from is carried out by loading guide, which is the loading guide is available in IEC standards, and also furfural analysis. This gives you the quality of the paper. The DP value of the paper in a good transformer will be over 1000. And if it falls below 200, the transformer is about to fail any time. Then certain trend analysis and OMM practices gives you the remaining life calculation. We move on to the health dashboard. This is the most important document which we get from the health assessment. Here, if you see, this one is superimposed on Google Earth. The location of the transformers are superimposed here. And then this is the fleet information. In the fleet information, here you can see multiple colors and some numbers are also there in this. So many number of transformers are good and so many numbers of bad. So these kinds of, it's a fleet level information that management knows you have so many good transformers, so many bad transformers which need to be attended. And this asset maintenance index is for people who are doing the actual maintenance. Here we give for a particular zone, how many transformers need to be attended as early as possible. Information is coming out from this. Additional information what you get is, this is the expected remaining residual life. So this particular case, it says 13 years more the transformer will live. Then there is something called an asset criticality index. This is a calculation based on a lot of factors like how important the transformer is, how critical the loads are. There are certain formulas for calculating this asset criticality index. And the next one is probability of failure is calculated. Then this asset criticality index and probability of failure gives you the asset risk index. So these are the information which goes for the top management and for the decision support systems. And decisions like whether you should replace the transformer, repair the transformer, upgrade the transformer are all taken based on the health assessment data. The benefits of health assessment is it's a decision support system, as I told you, and it can set the maintenance policy, whether you want to do corrective maintenance for low profile transformers, preventive maintenance or predictive maintenance. So predictive maintenance is what is done under condition-based maintenance. Then replacement policies are decided, which transformer to replace, when to replace. Lifetime extension, operating and upgrading requirements are done. This advantages of health assessment is a cost-effective improvement of system reliability. System reliability is dependent also on the design factors. As far as Qatar is concerned, 400 kV systems are N-2. That is, even if 2 assets fail, still the system will be stable. Below 400 kV, it is all N-1. One asset fails, the system can survive. So that design factor is also very important. And effective utilization of resources, because in the present day, the staff is very, very less compared to olden days. From 2000 onwards, if you look from between 2000 and 2005, the staff strength was reduced to 1/3, and the utility has increased their number of substations from those days. It was maybe about 120 substations, which went up to nearly 370 substations at 1/3 the staff. So effective utilization of resources, prioritization of maintenance, performing maintenance at the right time. And we reduce the forced outage and fault trippings. This can be measured using the reliability indexes like SAIDI and SAIFI, which are normally used in all utilities, which is the frequency, one is a frequency index, one is a duration index. This will be reduced with this condition assessment and condition-based maintenance. Thank you. And this was the basic information. And whatever I know, I can answer if you have any questions.
Thank you so much, sir. That was truly a great session. Sir, we have some questions in the chat box. Shall I read it out for you?
Yeah, sure. If I know it, I'll answer.
Sir. So first question is from Ravindranathan M. A very good failure analysis system to determine the root cause of failure. Corrective action for reoccurrence is seen and appreciated. Any specific quality system is followed, or can you slightly elaborate?
Quality systems are followed. That is basically management quality systems. It is not specifically for condition monitoring. There is no specific quality systems for the condition monitoring. There are past 55 systems, but which has not implemented in Qatar.
Okay, sir. Next question is from the same person, Mr. Ravindranathan M. Health status monitoring is just like that of a patient in ICU. Good. Your views about that. But here the patient is not in ICU, but healthy and performing well all duties as expected. And what is furfural analysis? Kindly elaborate.
Okay. See, patient need not be in ICU for inspection. The current practice is you go for an annual health checkup, whether you are sick or not. So the transformer is being continuously monitored, even if it is in good condition. Unless and until it's monitored, you never know at which point of time it's going bad. And nowadays you hear about executive health checkup, even if you are not sick. This is comparable to that. And there's furfural analysis. See, furfural analysis is basically, it's called a furan analysis, and it identifies the defects in the paper insulation. The paper, once it is damaged, it creates a compound called furfural, and there is a theoretical calculation based on furfural to find out the degree of polymerization, which is called the DP index. And this DP is the main factor for transformer failure. There are two ways of finding out DP. One is non-intrusive method like oil analysis, doing the furfural analysis, finding out the furan content. From that, extrapolating for DP. The second method is a direct method, an intervention method, where you open up the transformer, take a paper sample, and then measure the exact DP. And we have done both, and it's more or less similar. See, suppose DP, what you go from calculation was around 400. The actual DP was within the range of 350 to 450. And in a new transformer, the DP values are normally 900 plus 1000 in that range. And when the transformer slowly deteriorates, it falls, the DP falls. And once the DP reaches 200 or below 200, the transformer is ready for refurbishment or replacement. It can fail at any time. The insulation is very, very weak. I hope I'm clear.
Yes, sir. Thank you, sir. Next question. What is the typical lifetime of a transformer? And the question was from Dr. Ravindranathan KC.
It's a very, very difficult question to answer. Transformers follow the path curve. It can fail in the first 2 years. It may not fail for the next 50 years. So the first 2-year failures are mostly due to design deficiencies. And later on, there will be a stable period from 2 to say about 25 to 30 years. It's a stable period. 30 onwards, disease starts. And if it is well taken care of, we have had transformers which are 50 years plus. and which was replaced because of rating issues only, not because the transformer was bad. The old transformer, the design limits were very, very high. If you look at a new 100 MVA transformer and a old 20 MVA transformer, the 20 MVA would have been much bigger than the present 100 MVA transformer. So the design tolerances were there in old transformers. The new transformers, which came up beyond 2000, may not last that long. Second issue is the loading. How much load the transformer has taken in its lifetime. One particular case I can tell you, it happened in a company which was having a product which was having a very high market value at that particular point of time. So they wanted to produce maximum amount of during the peak value period, and they knew very well the transformers will fail. The transformers were operated at 120%, knowing very well the transformer is going to fail. But they started getting their product, product production was also about 120%. So the 20% excess, what they were able to sell at the peak price was better than even if the transformer failed. And as predicted, when the product prices started coming down, the transformers were all shut down. 7 transformers, the winding was totally replaced. So it's all a commercial decision. It is not only the life of the transformer, and a transformer which is very, very lightly loaded can last very long. So there is no specific life for a transformer.
Okay, sir. Thank you. And the next question is from Dr. N.N. Panikar. First of all, he has thanked you for the enlightening presentation. And the question is, where do we have the best practice in India?
India, I'm not aware of everything, but from supplier side, see, we have condition monitoring supplies coming from various parts of the world, and whatever information they have given is only what I have. What they have told me is Power Grid is doing all these condition monitoring activities in India. I don't have a direct information, but these are from equipment suppliers.
Okay, sir. So we also have some compliments in the chat box. Shall I read it out for you?
Yeah, sure.
Yes, sir. Highly technical presentation covering all factors. And thank you, Raghukumar, sir, for the wonderful coverage of all inherent risk and the ways and means to ensure the healthiness of transformers in a nutshell. This kind of talks will help the students in their quest for more knowledge in the subject. Excellent presentation. It has covered the whole scenario of loss prevention strategies available globally as far as the power transformers are concerned. Thank you very much, my dear friend, Dr. Raghu. I believe that was the last question. Does anyone have any other queries?
I'm glad to know that it is useful for the students.
Yes, sir. Thank you, sir. Sir, I believe there are no more queries. So one more query has come in. Is it advisable to repair a hermetically sealed power transformer without any special precaution?
External repairs, yes, you can do. But if you are touching the oil part, then getting the hermetical seal back is possible, but it needs expertise. Okay, we have done hermetically sealed transformer repairs, but external, mostly it was external. Even some internal interventions were done, but it's a very tricky part, and you should know what you're doing. And we have to follow the advices of the manufacturer to exactly to the point how to do it. It's not easy.
Okay, sir. Thank you so much, sir. You have patiently addressed all the queries that has come in the chat box. Thank you so much for that. Now I'd like to welcome Hannah to deliver the vote of thanks.
A warm and adorable evening to an adult gathered here. Most valued guest of honor, Mr. K. Raghukumar, all other esteemed dignitaries, and dear participants. I, Hannah Ansar of TKM Institute of Technology, is much privileged to propose a vote of thanks and acknowledge the contribution of those who worked hard to make this 93rd talk of Intersociety weekly webinar series a huge success. On behalf of IWWS, I exhibit heartfelt vote of thanks to our chief guest, Mr. K. Raghukumar, who spent his busiest time raising the occasion. Today, we had an opportunity to hear his words and thoughts, and this is going to encourage us in our future events, sir. Your thoughts are really enlightened us, and it was mind-blowing. As a token of love and honor, we would like to present you a virtual memento. Kindly accept it, sir.
Thank you.
Thank you, sir. A special mention to Harindra Lal, sir, respected chairperson of IEEE, being the backbone of this event, who inspired us to do our best and stand as a pillar of power. With deep sense of appreciation, thank you, sir. I would also like to express our sincere gratitude to the people who work behind the scene to execute this event, especially our technical arrangement team and Ms. Sandra, the moderator of the session, Professor K.C. Ravindranathan, who delivered the welcome speech, and Mr. Gogul, who gave the introduction of the speaker. At the end, I express my sincere thanks to all the participants who have gathered tonight. Your active participation was the success of this webinar. Thank you all.
Thank you, Hannah. Before we conclude, I would like to say one thing. The 94th Talk of Intersociety weekly webinar series will be held on 26th of January, 6 p.m. And the speaker of the day will be Professor A. Damodaran, IIM Bangalore. And the topic will be blockchain, the shape of things to come. Hoping to see you all on that day. With that, we are coming to the end of the webinar. Thank you so much.
Thank you, Raghu,
Thank you.
for a wonderful coverage. Thank you so much.
Thank you. And all thanks due to Harindra sir. I would not have given this presentation if not for him.
Yeah. Harindra sir is he's an inspiration for all people like us all the time.
Thank you, Raghu, for a great presentation. Very lucidly done, very clearly done. You also might not have expected that this might have come such a beautiful way. Thank you very much.
Thank you, sir.
Yeah, thank you. Thank you, sir.
The recording has stopped.
Okay. Professor K.C. Ravindranathan, please, up to you.
Shall I leave? Yeah. So the same student team will help me, or I have to find new people from section?
I can give you their email ID. You can.
Because I
will. No. Most of them are from EMBS. I think most of them are EMBS. You can consult them. It's not a big idea. You can get. I request all the student volunteers, if they are willing to continue, please give me a call or please give me a message. I will pass on to this team. Anyway, I will not press you because you have been supporting me for the last 2 years. I know that you have done this job with your pressurized
really
student.
great job.
So we will meet next meeting. Okay.
Thank you, sir. Shall I leave? We have executive
Good night.
Executive meeting from 7 p.m.
Thank you. Thank you.
Thank you, sir.
Thank you very much, sir.
Thank you, Shanmugan. Thank you, Shanmugan.
Thank you.
Rashda, you can close it. Thank you, Sri Umar.
Yes, sir.
Yeah,
Thank you,
thank you,
sir.
sir.